Alright, this is Ken Rosever. We're going to be doing confidence intervals, and these are going to be Z, ones that are based on a Z distribution. But let's assume you didn't know that. Let's assume that I'm going to jumble the order perhaps on the quiz. How would you tell that this is a Z and not a T? Well, this goes back to the previous problem, which was deciding on the proper distribution for making inferences about the mean. But maybe you haven't watched the video yet, so we'll just go through it. It says the lifetime of a certain brand of battery is known to have a standard deviation of 16 hours. So perhaps from past testing or something, they know that the standard deviation is 16 hours. And suppose a random sample of 150 such batteries has a mean lifetime of 36.1. So they sample 150, and the mean is 36.1 of the sample, so that is x bar. The standard deviation is 16 for the population, so that's sigma. And when sigma is known, we always use z. Okay, period. Especially when you have a sample size that's over 30, right? Anyways, they want us to find a 95% confidence interval. So before we do that, let me just give you a brief little background on confidence intervals. They just told me that the mean is of the sample was, what was it? I don't remember. 36.1. All right. Do I know the true mean of the population? No, I don't. But it's out there somewhere. There is a value around which the sample means are normally distributed. Okay, and so our sample mean is somewhere in there. If we want to come up with a 95% confidence interval, then we would imagine that we knew the mean. And if we knew the mean, we would find a z value that would cut off 95% of the population inside and leave only 5% outside. So 2.5% here and 2.5% here. Now the great thing is Alex has a calculator that does that, which you'll find if you do z of 0.025, it'll give you what this z value is that cuts off the upper 2.5%. Let me put percent there and percent there. Let's do it real quick. So I'm going to hit calculator. I'll just leave that where it's at, and I'm going to hit z of alpha, and alpha is my uncertainty on the top. Oops, let me clear that. And I'm going to put 0.025, and I think it's maybe 1.96. Yeah, it's 1.9599, whatever. It's 1.96 pretty much. So let me leave that there and go back here. So this z value is 1.96 up here, and it's also negative 1.96 here. So what is that saying? It's saying that within 1.96 standard deviations of this mean is 95% of the x bars. 95% of the sample means lie within 1.96 standard deviations of the actual population mean. Well, now we can flip that on its head, because we can say if this distance from here to here is, from here to there is 1.96, then if I just take that distance and I go wherever x bar is, and I go and I put x bar in the center. So let me scroll down. Let's say x bar is over here. Well, if I go 1.96 in either direction, look what happens. Is the mean within there? Yes, it is. The mean is inside that interval. Okay, so this is x bar plus 1.96 standard deviations, and this is minus 1.96 standard deviations, and it's in there. In fact, as long as x bars happens to be anywhere within this interval, and it will be in that interval 95% of the time, we're okay. It's only when x bar happens to be out here, which is very rare. That happens 1 in 20 times, right? When you have a 95% certainty, you have a 1 in 20 chance that it lies out here, that your X bar is actually one of those rare samples, one of those fluky samples that gives you a false indication. And when I'm out there and I go 1.96 in either direction, unfortunately, out there it does not capture the mean, okay? This is X bar. If it happened to be out there. But most of the time it's not. It's very rare that it is. So what a confidence interval does for us is, for whatever confidence level we want to have, it takes this distance, okay, which is appropriate to that confidence level, and instead of doing it around the mu, which is unknown, it does it around the x, which is known, the x bar, and basing it on that, we hope and we're confident, to whatever degree we have up here, that that distance about the x will capture the mu. It'll contain it. Okay, so it provides some borders. I hope that makes sense. I don't know if I'm explaining it the best, but I'm not exactly scripting this. So how do we do it? Basically, you find x bar and you add or subtract 1.96 standard deviations from each side. But remember, this is the standard deviation of the x bars. So that's actually the standard error. So you're going to have to do x bar plus z alpha, and then what's sigma for the x bars? It's sigma divided by the square root of n. So that'll be your upper limit, and your lower limit will be the same thing, minus z alpha. Oh, alpha over 2 actually, because I took the 5%. Alpha is our percent uncertainty, which was 5%, because if we're 95% certain, we're 5% not certain. And alpha is our percent uncertainty. It's actually the chance of being wrong. And we're dividing it by 2 because we're splitting it on both ends. So it's z alpha over 2 times sigma over the square root of n. Okay, so you can see also why you have to know sigma, because if you don't know sigma, you can't use z. All right, different formula. So let's finish it up. Here we go. Let me chime check. We're okay. So if I want the upper limit, let me store this. I do my mean, my sample mean, which was 36.1. And actually I can hit plus or minus and it'll get both of them for me. Plus or minus, let's recall that, 1.96 times my standard deviation, which is 16, divided by the square root of 150. And that'll get both of my answers. And you can see them, 33.539. We want it to 3 decimal places, so I'm going to look one more, and it's a 5, so I'm going to say 33.54. It's the lower limit. And the upper limit is 38.6604, so we'll just call that 38.66. So, oops, 38.66. And I'm going to hit next. All right. Before I do another one, let me just point out one little thing here. This right here, this term is called the error, because what we really have when we do an interval estimate is we have our point estimate, which is x bar, plus or minus our error. Okay, and our acceptable error is based on our confidence level, and we can adjust, we can figure out how big our sample size should be so that our error is reduced to whatever what do I want to call, precision we would like, to whatever degree of precision we'd like. If we'd like to be only off by 0.5, we can make that happen by picking an appropriate sample size. I'll do another one on another video. Okay.